Let us start a new section, section 4.2. So here we are going to develop the system of rational numbers. Just like in the previous section we developed the system of integers. Let us briefly recall what we did there. We defined integers as formal differences of natural numbers, and we used an artificial symbol, a notation to denote the integers, where we used a long horizontal bar. On that set of such symbols, we then defined an idea of equality, a concept of when two integers are supposed to be equal, and then on that set, with that equality relation, we defined addition and multiplication, the two basic operations. We then proved all the basic things regarding addition and multiplication. Then we defined a new operation, namely the negation of an integer, and using it we then defined subtraction of two integers, which ultimately allowed us to get rid of that artificial notation and write an integer as an actual difference of two natural numbers. And finally, we defined an order relation on the set of integers, and we proved the basic properties of order. So these are the things we did in the system of integers. Now exact similar things we are going to do here in developing the rational numbers, or the rationals in short. Okay, so now we already know informally what rational numbers are. They are expressions of this form which are called quotients of integers, where a and b are integers, and the usual caveat is always there: the denominator b is non-zero, it's not equal to the integer 0. Let us briefly discuss why we have this. You see, division by 0 in mathematics cannot be meaningfully defined. For actually it can be defined, but if you forcefully define it, then you have to compromise by not having some useful laws that we have become accustomed to in the system of say rational numbers or real numbers, with which we are actually already familiar. And one of those laws is the cancellation law with respect to multiplication. You see, if we have, let me just discuss it in the context of real numbers themselves. Say a, b and c are three real numbers, and we have ab equal to ac, and also at the same time we have a non-zero. We then know that we can divide by a on both sides. That gives us b equal to c. We use this law, cancellation law, so many times, and we keep using it that we don't even bother to check in many instances that this should be non-zero, and that leads to many different types of errors. That is a different thing altogether, but the thing is that this useful law is present. However, this law will no longer be true if division by 0 is possible, because you see, we have 0 times 1 is 0, and 0 times 2 is also 0. Now if division by 0 is forcefully defined and we have this, then we no longer have the cancellation law. See, this does not imply that 1 is equal to 2, because 1 is not equal to 2. Okay, so the cancellation law is not there anymore. So the resulting number system that you end up with, if division by 0 is forcefully defined, is not very useful. It will have some of its own properties, but it's not very useful, and it's certainly not the one with which we are familiar. Okay, so that's why we have this condition. Having said that, I should add that although division by 0 is not allowed, but we will see that division by a quantity that approaches 0, that is very small, is allowed, and in fact is the essence of analysis or calculus, which actually allows us to define the concepts such as limits, differentiation. This type of things can be done because of such a concept. So we will see that. Okay, now coming back to our actual discussion, we are going to define rational numbers just like how we defined integers from natural numbers. We already knew that integers are differences of natural numbers, but we were not able to use actual difference because that would be circular. So we had to develop this artificial notation by using a meaningless symbol, which we also interpreted as something like a scaffolding when a building is constructed. A similar thing we have to do here. We will not use actual division, but we will rather use, or in another alternative notation, we also write a quotient like this now with this slash. So instead of that, we will use this meaningless symbol, double slash, to denote a rational number where a and b are integers and b is non-zero. Then we will proceed just like how we did in the case of integers, and eventually we will define division, which will help us get rid of this meaningless symbol. So it plays the same role that this horizontal bar played in constructing the integers from the natural numbers. Now we are going to construct the rational numbers from the integers, and the pattern will be the same that we followed there. So we already know what to do, and because of our previous knowledge with the rational numbers, while defining the operations of addition, multiplication, negation, etc., we will already know what the definitions are supposed to be. Okay, so with that, let us start with the definition. And the definition goes like this. A rational number is an expression of the form this, where a and b are integers and b is not equal to the integer 0. We do not assign any meaning to the symbol this. If the second component, this symbol, just like the symbol for integers, has two components, a and b. If the second component is 0, we do not assign any meaning to such a thing. For us, this situation is undefined. We don't care. Okay, so yes, the condition for equality of two rational numbers is a part of this definition. Two rational numbers a by b. We continue to call it a by b or a divided by b. Okay. Are defined to be equal, that is equal to this if, okay, normally when do you have this? Clearly when and only when AD is equal to CB, and in this condition we don't have anything new. We already have what we developed in the system of integers, namely product of two integers and equality of two integers. So that will be the condition which will define this equality. If AD is equal to CB, just like in case of integers we had the condition that a plus b is equal to c plus b. Here in place of plus we have product of integers. The set of all rational numbers is denoted by Q, where Q stands for quotient. So for instance 3 by 4, this is a legitimate rational number. 3 and 4 are integers and 4 is not equal to 0. This will be equal to 6 by 8, because 3 times 8 is 24 and 6 times 4 is also 24. So that's why by the definition of equality they are equal. And this is also equal to minus 3 by minus 4. That's because 3 times minus 4 is equal to minus 3 times 4. So that's why these rational numbers are equal. But 3 by 4 is not equal to 4 by 3, because 3 times 3 is 9, but 4 times 4 is 16, and they are not equal. We already know that. This is a valid definition of equality. And by now you already know what we mean by this. Such a relation is a valid definition of equality if it is reflexive, symmetric, transitive, and it satisfies the substitution axiom. So this will be handled in exercise 1. Okay. So now next we are going to define the basic operations of addition, subtraction, addition, multiplication and negation, because we have already come across negation. Before defining negation for the integers, it was not there in the system of natural numbers, and that is because if we negate a natural number, we don't get a natural number. Okay. So that's why that was not defined at that point, but after having integers, negation is now an operation. So we are now going to make these definitions in the next definition. if A by B and C by D are rational numbers, then we define sum of A by B and C by D to be the rational number AD plus BC by BD. Product of these two rational numbers. The definition of product is easier than the one for sum. AC by BD, and the negation of A by B is defined to be this. You can understand where these definitions are coming from. A by B plus C by D, without saying anything more about this expression, is we already know from our experience with rational numbers that is equal to this. Just like that, this is equal to AC by BD, and minus of A by B is equal to minus A by B. So from our prior knowledge of these things, using that knowledge, we have been able to make these definitions. Okay. Note that since B and D are non-zero. Why we say B and D are non-zero? It's because it is given that A by B and C by D are rational numbers. So by definition, B and D are non-zero integers. We have the integer BD also non-zero, and this actually follows from proposition 418. So AD plus BC by BD and AC by BD are legitimate rational numbers. So you notice that, okay, this was just for the discussion. Okay. So you notice that even for the definitions to make sense, that whatever we have defined these operations to ultimately be equal to, we need proposition 418, which was that one which says that integers lag zero divisors. That if we multiply two non-zero integers, then we are going to get non-zero integer. So that proposition has been used here in an essential way, without which we cannot define it the way we have defined rational numbers, namely where the second components always have to be non-zero integers. But we still have to verify that these definitions are well defined, namely that if we replace, for example, the rational number a by b by an equal rational number, the sum is not affected, the product is not affected, and the negation is not affected, things like that. So for that we have the next lemma. It is because of these small things that we have to, while developing a system, we have to carefully do it. If we are carelessly just following whatever prior knowledge we think we know about these systems, then we are bound to get something wrong. Okay, the lemma goes like this: the sum product and negation operations on the rational numbers are well defined. In the sense that if we replace a by b with another rational number, a prime by b prime which is equal to a by b, then the outputs of the above operations remain unchanged. And similarly for c by d, instead of replacing a by b with an equal rational number, we can also replace c by d with an equal rational number. That also will have the same effect, namely it will have no effect at all on the outputs. So the proof, naturally a part of the proof will only has only been done in the text, and the rest is left to us for in the exercises. So we just verify this for addition. we leave the remaining I forgot the spelling of remaining claims to exercise 2. Okay, so that means in this case we have these two equal rational numbers. We have to show that the sum of this one and c by d is equal to the sum of this one and c by d. So assume a by b is equal to a prime by b prime. Then by the definition of equality of two rational numbers, this is equivalent to having a b prime equal to a prime b. Now we need to show this a by b plus c by d is equal to a prime by b prime plus c by d. That is, if we apply the definition of addition, then this is the same as AD plus I need some ink. AD plus BC divided by the, I may have to come back to this, should be equal to A prime D plus B prime C divided by B prime D. This is AD plus BC divided by BD, and this is A prime D plus B prime C. So that means these two things have to be shown to be equal. That is, we are simplifying the things, reducing them, applying all the definitions, and we want to get to the actual thing that we have to show. Now you apply the definition of equality. So this is equivalent to this. This in turn will be equivalent to AD plus BC times B prime D is equal to BD, or this will come first. It doesn't matter which one we write first, but just for the sake of definition, let us write it how it's given in the definition: B prime C times BD. That is, now this is a statement that uses only the elements in the system of integers. It has addition and multiplication of integers, and it has equality of two integers. So that is AD B prime D, or we can write at once A B prime D square plus bb prime cd is equal to a prime b d square plus bb prime cd. And you can see that this last equation is true because these two terms are equal integers, and here in the first terms we have d square which is there in both the terms, but other than that here we have a b prime and here we have a prime b. So from this equation they are equal. This last equation is true because a b prime is equal to a prime b. So this is what we needed, and this is true. So now you can do the back calculation. You can multiply both sides by d square, add this integer on both sides, and you follow the argument in the other direction, you will get what you want. And similarly for c by d, if instead of this side, if someone replaced c by d with an equal rational number, then also addition will not be affected. So here incidentally the symbol with which I end a proof, that happens to be the same as our current symbol for division. And the other identities or the remaining proof will be handled in the first exercise, or second exercise. Okay, now we immediately come to the issue of identifying integers inside the set of rational numbers. Just like how we identified natural numbers inside the set of integers, we identified any natural number with the integer that looks like this. So a similar thing we are now going to do for integers and rational numbers, and we are going to do it like this. We note that the rational numbers a by 1 behave in a manner similar to the integers in this following sense. If we add two such rational numbers, then according to the definition of this sum, it will be a times 1 plus 1 times b, that means a plus b by 1 times 1, which is 1. This one is easier. The numerator, if we say like that, although we should not actually say the numerator of a rational number. Exactly why that is so, we will see. Okay, in this case numerator is, if you want to say numerator, just say numerator, don't say the numerator. AB by 1 times 1, which is 1, and the negation is just like minus a, just like the natural the integer minus a. Also, one more thing is there. These two rational numbers are equal if and only if. Apply the definition. A times 1 should be equal to 1 times b. That means a should be equal to b. So we see that if we identify the integer a with this rational number, then all the algebraic operations as well as the concept of equality stay consistent. There is nothing essentially changing, and we can through that identification identify the whole set of integers, or in fact the whole, I should not only say set of integers, but the whole system of integers with all its algebraic operations as a subsystem of the system of rational numbers, because there is a subsystem of the system of rational numbers that behaves